ether theory stayed popular for so long.
Okay.
There was a German physicist by the name of Encke, Hans Frank Encke, I think his name was.
Okay.
And what Encke, Johann Franz Encke, what Johann Franz Encke noticed, it was around 1830 or so, he began to watch a comet going through the solar system. Now, as soon as I say comet, you're going to say, Joel, Halley's Comet only shows up every 75 years. Yeah, but Encke's Comet showed up every 2 years and 3 months.
Okay.
It was a real quickie. It moved through the solar system on a period of 2 years and 3 months. But every time it reappeared, it showed up like about 2.5 hours sooner than was predicted for it. Now, Encke gave a big, long mathematical treatment to this, and he said, aha, that proves an ether, because what's happening is this comet is encountering friction in deep outer space,
and down.
The friction is pushing it closer to the Earth. But see, even that's ridiculous. It's counterintuitive, because he's saying the friction slows it down, but then it shows up sooner, but then it's moving faster.
Right, okay.
So let me tell you how Encke covered that. Encke said, well, look at Venus. Venus is moving faster than the Earth. So that means, in other words, he said, well, so it's not counterintuitive. Okay, now, Encke's comet was always there from the early 1830s until the 1900s, when all of a sudden Encke's comet stopped squirting off water, and it stabilized its mass. It didn't get any lighter, and it started showing up at exactly the same time.
Interesting.
So as soon as it started showing up at exactly the same time, you lose your ether. You see why that is? If it's keeping if the comet is keeping perfect time, there's no friction.
Okay.
If there's no friction, then there's no ether. There's nothing pulling that comet back. But there could have been.
Is there somebody on your end playing a radio? Okay.
No, I don't know where that came from.
I don't know where it's coming from either.
Okay, so in other words, the image of an ether was perfectly legitimate up until I don't know when Encke's comet stopped doing this, but there was a scientist whose name was Frederick Wilhelm Bessel, who was he was a little older than Encke. And he said, well, maybe Encke is just squirting off matter like a geyser. But that idea just fell to the wayside because this ether theory became popular.
Yeah.
But then in the 1950s, a guy named Fred Lawrence Whipple said, I think Encke's comet is squirting off matter. And that was actually proven. There is now photographic images of geysers squirting off of Comet Encke. So, in other words, the ether theory was tenable. It couldn't be disputed based on the motion of Comet Encke until Comet Encke stopped showing up earlier, and that didn't happen for almost 100 years.
Okay.
And then the final blow was when there was film footage of Encke squirting off with having having volcanic activity.
And that's what comets normally do. Isn't that what the tail usually consists of, is a lot of cast-off matter, ice, and what have you?
I am not a complete authority on astrophysics.
Okay.
I don't know everything. Generally, what happens with a comet is when they first show up, they're shiny, and then as you watch them year after year, they get duller and duller.
Right. Okay.
And somebody like me would interpret that to mean that water is being melted off when it goes near the sun.
Okay, but the basic point you're making is that the friction idea doesn't hold up.
No, not anymore.
Okay.
There was only that one. So you have to understand the arcs of the cycloid, all the curves that I'm telling you about, were just sort of like ignored because there was no reason to use them. Now, let me
go ahead.
Okay. Now, let me tell you a shortfall with this. When Niels Bohr gave his Nobel Prize speech in 1922, he said, what we're looking for, Niels Bohr's idea was that electrons go around the proton in planetary-style orbits.
Yes, that's the familiar concept of an atom. Yes, okay.
Yes, but the problem with that is when you look at the spectra for a particular element, it shows sharp bands.
Yes.
It doesn't show a continuous variability. You would expect the electron to move in and out at any given radial orbit, but they never do that.
Okay.
Now, if you substitute for planetary orbits, which are either circles or ellipses, if you start plugging in the cycloids, the variance on the cycloids, it's the common cycloid and the kurtate cycloid are completely discontinuous, as is the prolate cycloid. So you get three variants that are absolutely distinct. So now you can start talking about sharply distinct bands. Now wait, it gets better than this, Pastor.
Okay.
Let me give you the punchline here.
So kind of like tubes in space. Is that where we're getting? Is that where we're going?
Well, I wouldn't say tubes. I don't know why you would see an image of a tube.
Yeah, I'm picturing the cycloid going around the sun. So maybe I'm picturing the wrong way. But go ahead. Yeah.
Okay. Now let me give you the best issue of this is, if you take the cycloid, you predispose that a cycloid is constructed by a mix of an electric and a magnetic field, and those fields have a certain orientation to one another. Yes. Maybe they're at 90 degrees, maybe they're at 45 degrees, but they have an orientation. Now, if you switch the orientation and the intensities of the fields, you can get linear motion. Okay. You can get up and down motion. So the sharpest lines in the spectrum of any given atom are doable off the cycloid, because you can solve the equations in such a way as to get a straight line. Yes. You can also reduce a cycloid to get an ellipse, and an ellipse is only a more complicated form of a circle. Yes. So when I say to my audience, let's start thinking cycloids, that doesn't throw out the circle and the ellipse, because the circle and the ellipse are variants on the cycloid given certain intensities and arrangements of the electric and magnetic field. Okay.
Now, where does that leave us vis-a-vis waves and particles?
My supposition would be then that electrons always stay waves. They're always waves. But under certain circumstances, if the mix of the field is just right, they're moving as a kurtate cycloid. Okay, which and that would give you the up and down. Yes, that would give you the up and down undulation, and then I would say that all the confusion, all the mysterious things that are attributed to light, could probably be explained away just by a reanalysis with an application of the various forms of the cycloid.
Okay, all right. So we have the cycloid mechanics. How does that now impinge upon the theory of relativity? That we obviously, for example, when you're sitting at a train station and the train on the other side of the track starts moving away from you or whatever direction, it feels like you're moving, but when you're really not. And that's what I consider like a classic form of relativity, that you can't even tell who's moving and which side is standing still. So what are the forces that determine this relativity field?
Okay, now what you're asking me about the Doppler effect, and you're basically saying, Joel, a train is moving towards me, and the train engineer toots his horn, and the horn has a real high pitch. Yes. And then when the train passes me and goes away, the pitch drops. Yes. Now, what happens there is simple checkbook arithmetic. Okay. When the train is moving towards you, the sound wave is moving at its own speed, plus it's moving at the speed of the train. Yes. So if the train is going 50 miles an hour and the speed of sound is 200 miles an hour, then you've got an undulation moving towards you at 250 miles an hour. Okay. And when it passes you, then the sound is coming back to you at 150 miles an hour. Okay. So your ear can detect the difference in the pitch. Right. Now, when you get into light motion, when you get into the motion of light, that checkbook type arithmetic works, but sometimes it doesn't work. Okay. And then they invoke relativity theory. Ah, okay. So in other words, when things don't add up, when you end up with a Bernie Madoff type of algebra situation, right. when something's missing, then people say, okay, Einstein was right. But it's not necessarily that might not be true. So it's not that simple. It might be the difference in the difference between a kurtate cycloid and a sine wave is causing this amount of variability. Now, let me take you someplace fresh. Okay. The Lorentz contraction. When this fantasy developed that electrons gain mass when they go faster. Right. Yeah, I've always found that hard to believe. Okay, go ahead. Yeah, Lorentz solved an equation to that, an algebraical, And he said, okay, watch out, because those electrons, when they get to the speed of light, they're gonna be infinitely heavy.
Right.
But he didn't. That's because his equation was only valid over a very short portion of the dynamic range.
Okay.
I resolved that process to the hyperbolic tangent and showed that the mass, even if there was a mass, which I don't believe there is, that it would have an upper and lower bound.
Yeah.
Now, let me tell you how dangerous that is.
Yeah.
When you start saying that if an electron goes at the speed of light, then it would be infinitely heavy, and it would drop on you, and it would crush your feet when it hit the floor. Now you're saying is that light has to be something different from an electron.
Mm-hmm.
So now you open the stage door for Einstein to walk on and say, whoopee-doo, I'm going to invent the photon.
Right.
So
Okay.
the photon was real in Einstein's mind, and he forced the rest of the world to believe in photons.
Interesting.
Because he said, well, what would happen to an electron if it went at the speed of light? It would be infinitely heavy. Therefore, there must be something called photons. I think a photon is nothing other than an electron moving at the speed of light, and I don't have. In fact, there was a Nobel Prize winner who just died last year, and excuse me, I'm not. I want to keep talking forever, but I'm getting a little hoarse.
Need to get a glass of water or something?
No, that's okay. The Nobel Prize winner, his last name is Lamb, Willis Eugene Lamb. And in 1955, when Willis Eugene Lamb accepted the Nobel Prize, he said, I'm going to quote from a Nobel Prize winner now. He said, I have heard it said that the finder of a new elementary particle used to be rewarded by a Nobel Prize. But such a discovery now ought to be punished by a $10,000 fine.
Right.
So, you see, Dollmayer is not, I'm not David pretending to be insane in the wilderness. You understand? I'm not spitting on myself and scratching myself and clawing at myself. I'm quoting from Nobel Prize winner.
Right.
Willis Eugene Lamb, he probably had blue eyes. He said in 1955, this business of subatomic particles is screwy, and we need another way of explaining things.
Interesting.
And that's what I'm doing. I'm not coming up with this. This is not something where I heard voices and they told me to try the cycloid.
Right.
A Nobel Prize winner said, we're taking the subatomic particle nonsense way too far, and it doesn't make any sense anymore.
Yeah, well, the ancient metaphysical concept that's true of, well, what I call the Aryan philosophy, the oldest philosophies I'm aware of, say that all is vibration, which means it's waves. Everything is composed of waves, and that particles, the particulate world, is an illusion. It's really waves. It just appears to us as particles. What do you say to that?
Why can't particles be moving in a way so that they look like waves?
Sure. Exactly. Well, the question is, are particles real, or are they simply an illusion that's created by the as in your case, by the cycloid motion?
No, I think the waves are what's illusory.
Oh.
And I think that now let me tell you something that's fascinating called Cherenkov radiation. When you look at if you ever watch any science fiction movies, whenever they have a scene of a nuclear reactor, they always show the water bath around the reactor as being a beautiful shade of blue.
Okay.
It really is that shade of blue, and that shade of blue is caused by something called Cherenkov radiation.
All right.
Now, here's what I think. What I think is that when electrons start coming off a nuclear reactor, at first they're moving at a very fast speed, somewhere near the speed of light. And then when they get into water, they slow down because water is rubbery. It has a jello-like consistency for an electron.
Yes.
So I picture electrons moving like over the arc of the Curtate cycloid when they're in a vacuum, but then when they hit a medium like water, then I think they start oscillating like a sine wave up and down because